Good afternoon. It's a pleasure to be here, and thank you for the organizers for organizing this very nice conference and giving me the chance to present here. So I'll tell you about experiments we're doing at Princeton, where we're studying a Fermi-Hubbard system and looking at transport phenomena in it, and we've seen some very interesting behavior. So before I tell you about transport in a strongly correlated regime, which we are interested in, let me start by telling you more about probably what you know, transport in weakly interacting systems first. So in a weakly interacting system, we can describe the system by quasi-particles. And so all the quantities that we transport, like charge and spin and energy, are transported by these quasi-particles, which are moving around and scattering off each other at some rate gamma. That we can also connect to maybe a mean free path between collisions through this Fermi velocity. So now in a good metal, this mean free path will be pretty long. And as we increase the temperature, it will start to shrink. And if we're working in a clean system where there's no disorder, and if we assume there's no phonons, as is the case in our experiments, then this mean free path can be bounded. So clearly, it cannot be shorter than the interparticle spacing. And maybe in a lattice system, an even more strict limit would be to say it cannot be smaller than the lattice spacing itself. So these bounds go by the name of the Motiaf-Viragel limit. So there's people use different conventions for different definitions. But I'll be using this talk, the definition that the mean free path cannot be shorter than the lattice spacing. OK, so if we now start to heat up a system, and we assume the only scattering is due to interactions, then we find that the resistivity, as predicted by Boltzmann theory, by the Boltzmann equation, would go like T squared, the temperature squared. And eventually, it would saturate at this a bound that's given that we can infer from this MIR limit. So of course, mean free path is something difficult to measure in a condensed matter system. So usually, experimentalists measure resistivity, and they can use that bound to put a maximum possible resistivity that you can measure. So that's the situation in a weakly interacting system. In a strongly interacting system, once you introduce strong interactions, you destroy the quasi-particles. And since now we can no longer use Fermi liquid theory and the Boltzmann equation, now we do not have a good framework for calculating transport. So one has to resort to maybe exact techniques on small systems. OK, so in the strongly interacting systems, we can have, like the cuprates or the pnictides, experimentally one observes what's known as bad metallicity. So this is defined as a violation of the MIR limit. So as you increase the temperature, the resistivity can increase beyond the MIR bound. And commonly in these materials, the resistivity actually, instead of scaling like T squared, it scales linearly with the temperature. So of course, in a cold atom system, we can try to go and look for this stuff because we can control the interactions. And there has been indeed a lot of previous work looking at transport in strongly interacting fermions. There's a lot of beautiful work from the group of Tillman Esslinger in Zurich, where they tailor optical potentials. So they have reservoirs connected by channels, and they can look at mesoscopic transport in these systems. And more recently, there has been studies of bulk transport. I want to highlight these two experiments from Brian DeMarco's group and from Joseph Tyvison's groups in Toronto, because they're connected to our work in that they're using also lattice systems. OK, so the playground I want to use for exploring transport in a strongly interacting regime is the Fermi-Hubbard model. So we have in the lab a 2D lattice, a square lattice, where we put two species of fermions. And these fermions can tunnel around between nearest neighbor sites, as described by the first term of this Hamiltonian. And whenever two fermions of opposite spin land on the same site, there's a strong repulsive interaction. Now, this Fermi-Hubbard model, of course, has been studied for a very long time, but we still don't know its low-temperature properties. But if it was proposed a long time ago by Anderson that it can describe the cuprates, so we can if we assume it does describe the cuprates, we can maybe cheat a little bit and learn about the phase diagram by looking at the cuprate phase diagram, and hopefully the Hubbard model has a similar one. So here's a phase diagram in the temperature and doping axes. So what's understood theoretically very well is the undoped regime. So at high temperatures, but below the interaction energy scale, you get a Mott insulator, and then as you lower the temperature, you get antiferromagnetic correlations. So this experiments have seen in cold atoms, of course. But where less experiments have happened and where what's less theoretically understood is the doped regime. So there's a lot of effort trying to reach at low temperature equilibrium phases, like say pseudo-gap phases. But there are actually high temperature phases, like the strange metal at finite doping and relatively high temperatures, which are not described by equilibrium quantities, they're described by transport properties, which one might hope to see first. So for example, in the strange metal phase, like the bad metals, there's a linear in temperature resistivity. So we thought, okay, let's see if the Hubbard model can see some of this phenomenology. So our setup is a quantum gas microscope, similar to the one that Christian talked about. It's also a lithium microscope. And so we have a 2D system, a 2D gas of fermions, in which we load adiabatically into a square lattice. And when we want to image the state of the system, we just freeze the density distribution in a very deep lattice and scatter photons in Raman cooling configuration. So we can collect roughly about 1,000 photons per second and get images like this, where during the exposure time, the hopping and loss rates are at the percent level. Okay, so let me tell you now about the transport experiment we've done. So we're interested in measuring bulk resistivity in the system. And we want to do a really clean experiment at a fixed doping. And in cold atom experiments, usually the density is varying due to the presence of a harmonic confinement because of the Gaussian lattice laser beams. But in our experiment, we have actually flattened the trap near the center using a spatial light modulator. So we send light that an extra repulsive potential that produces a flat trap in some region of the cloud. And so we just have a Hubbard system with a uniform density. And then on top of that, we add a long wavelength sinusoidal modulation that you can see even in these single shot pictures here. You can see stripes along one direction. So this is something we, again, send through this micromirror device, so we can control the wavelength of this sinusoidal modulation anywhere from a few sites to the full system size, which is about, here, a diameter of 30 sites or so. Okay, so the idea behind the experiment is we load the system adiabatically, so we have the lattice and we have this long wavelength modulation, and now we suddenly switch off just the long wavelength modulation. Okay, but we let the system now equilibrate in this lattice. Okay, so the fermions start to diffuse, and eventually we lose the contrast of this modulation. And from the diffusion, I want to show you how we can, from these measurements, we can extract a diffusion constant, which is a microscopic quantity characterizing the transport. And we can link this to a macroscopic quantity, the resistivity, using the Nernst-Einstein relationship. So what that tells us is that the inverse of the resistivity, the conductivity, is the product of two quantities. One is a diffusion constant, which is a dynamical quantity. And the other is the compressibility, this derivative density with respect to chemical potential, which is a thermodynamic quantity. So this quantity people have been measuring in cold atoms for a long time. The new part is measuring the diffusion. Okay, so here's the raw data. So we have this trap, and we flatten it in some region, and then we put this long wavelength modulation. So that's the flattened trap is in here, this elliptical part. And the doping is roughly 20%, so density is 80% per site on average. And then we have this one-dimensional pattern. And so here it is integrated along one direction. So here I'm just showing the density of the up spin, so multiply by 2 to get the total density. And now this is just before we switch off the pattern, and then we switch it off, and it starts to decay, this contrast. And it happens very quickly. So this is 50 microseconds later. This is 500 microseconds later. And OK, so we can fit this amplitude of this sine and track how this amplitude decays versus time. So here's this amplitude plotted versus time for a strongly interacting system, U over T roughly 7 or 8. And the density is 82% plus minus a few percent. OK, so this is for a modulation which is relatively short wavelength, 5 sites. And you can see that we see a bit of an oscillation, an under-damped oscillation. So this was for 5 sites. Now, for a modulation of 10 sites, it becomes a bit more damped. For 15 sites, even more damped, and completely overdamped at 20 sites. You could almost fit this to an exponential decay at that point. OK, so that's the kind of data we take. And the curves that we're putting on top of this is a simple fit. So we're using just 2 fit parameters. These fit look like a damped harmonic oscillator. So we fit the frequency of the oscillator and the damping. OK, and all the curves, the fit works with a single frequency and a single damping. OK, so here's our motivation for that. We have a simple hydrodynamic model that gives this form. So 2 equations. The first one is a simple charge conservation equation, which obviously has to hold. The second one is more of a phenomenological equation. So the idea here is that your first step might be to say, OK, the current is proportional to the gradient of the density through the diffusion constant. So that's Fick's law. Well, what that would give you is an amplitude that decays exponentially in time. So that correctly describes the long wavelength behavior. Now, we clearly see that there are some inertial effects going on. We see like this change here in the sign of the amplitude. We see some curvature in the beginning. So that's not compatible with Fick's law. Fick's law tells you there's an instantaneous change in the current. So we kind of have to make the current change a little at some finite rate. So we introduce the rate of the change of the current reaches its equilibrium value in some time scale, which is the inverse of this gamma. So this we would call a current relaxation rate. OK, so there's 2 parameters here, the diffusion constant and the current relaxation rate. If you combine these 2 equations, you get a second-order differential equation for a damped harmonic oscillator with damping gamma and a frequency squared, which is this gamma d k squared, where k is the wave vector of the modulation. So, OK, so we can now, from knowing the frequency of the oscillator and the gamma, we can extract these 2 microscopic quantities. And you can see that since this frequency depends on k, then there's a crossover, as we saw here, from a diffusive case to an underdamped sound. OK, so we've measured this diffusion constant and this gamma. And now the interesting thing is to see how they depend on temperature. So we've taken data the same way at different temperatures. And here's the data. So you can see that the diffusion constant goes down as you increase the temperature, and gamma goes up, just as you would expect. The scattering rate increases for increasing temperature. And at low temperatures, the polyblocking closes the scattering channels, so you expect D to go up. Now, the error bars on gamma get pretty large at high temperatures because, as you saw, at high temperatures, you just get an overdamped oscillation, so it's hard to fit both gamma and D. OK, so now the first interesting thing to note here is that you could look at how this diffusion constant compares to what you would expect from the MIR bond at high temperatures. So the MIR bond is, of course, on the mean free path. It says it cannot shrink below the lattice spacing, but we can convert that to a limit on the diffusion constant by just multiplying by some velocity, typical velocity. And so that's the dashed line here. And we can see that we're approaching the MIR bound in the diffusion constant, so no violation there. OK, so now to convert to a resistivity, the second quantity we need to measure is the compressibility. And this is something that the cold atom community knows how to do. So you can put the system in a harmonic trap now and measure the density profile and take the derivative of density with respect to the local chemical potential. And so we've done that. And so here's this compressibility plotted versus temperature. And since this is a thermodynamic static quantity, we can actually do Monte Carlo calculations down to the lowest temperatures that we can access with the experiment. So for these experiments, we've scanned a wide range of temperatures, all the way from about 4% of the bandwidth to 8T, which is the full bandwidth. OK? So it agrees with the theory. And what I want to emphasize here about this plot is that there is a prediction we can make for the high temperature limit of the compressibility. And at very high temperatures, the compressibility goes as the inverse of the temperature. And the key thing I want to point out here is that we are not in the high temperature limit. You can see our measurements are very far from the high temperature limit. So the high temperature limit really holds when your temperature is large compared to the bandwidth, and we're not in that regime. And the reason I point that out is that one simple way to get a linear anti-resistivity that was pointed out a long time ago by David Hughes is that you can get a linear anti-resistivity just purely from the compressibility at high temperatures. So if you go to very high temperatures, then this compressibility goes as 1 over T. The diffusion is supposed to saturate the diffusion constant, so then you would get a linear anti-resistivity, but we're not in that limit. What you can see is there's a non-trivial temperature dependence for the compressibility, a non-trivial temperature dependence for the diffusion constant, and now here comes the magic part. When you go and combine these two things together to get the resistivity from the Nernst-Einstein relationship, those dependencies somehow combine to give you a linear anti-resistivity over this wide temperature range, which is in this, what I would call the intermediate temperature regime, because the temperatures are kind of below the bandwidth. OK, so that was one thing that caught us by surprise, this linear anti-resistivity. We can characterize the linearity in different ways. We can fit to power laws or fit to kind of a line plus quadratic component. And it's a pretty good line. So another thing that might be interesting to look at is how this resistivity compares to the MIR bound. So again, we can infer an MIR bound from the mean free path to the resistivity. And for the resistivity, the bound would be this expression here, which is the gray line. And we go through the MIR bound. So this part is not so surprising, going through the MIR bound, because we're accessing a regime which condensed matter experiments don't typically access. We're going to very high temperatures where the compressibility is actually changing, right? And so this dependence of the compressibility at high temperatures would already give you the violation of the MIR bound. But what is really interesting, I think, in our experiments is the linearity here. OK, so as I said, we don't have a good way to understand this linearity because the system is not in a quasi-particle regime, so we can't use our usual toolkit. But we can do comparison to numerics. So here's a comparison to an exact theory, finite temperature Lanczos, on a 4x4 lattice. And so this calculation takes about a month to do. And so since this is a finite lattice, you run into finite size effects, and those become more and more severe as you lower the temperature of the system. So for the system size we chose, we can only go down to T about roughly 1 tunneling energy scale before we run into finite size effects. And this is a parameter-free comparison, so you can see that it agrees pretty well with the data. OK, so now, of course, our experiment is reaching about a factor of 3 lower than the temperatures where you can do these calculations. So we've also compared to dynamical mean field theory. And you can see the dynamical mean field theory, which is a huge approximation, of course, it lies off the exact calculation in the data. It actually has some features which are not in neither the exact calculation or the data. It has a kink in the resistivity, which was emphasized in previous work from Antoine Georges, and we don't see that in our data. So to summarize, we've seen this violation of the MIR bound, but we understand it comes from the static part, the compressibility. But the more interesting part, maybe to understand how that comes about, is this linear dependence of the resistivity from a non-trivial combination of the diffusion constant and compressibility scalings. And we have started now testing these, benchmarking these approximate techniques like dynamical mean field theory. And I think that's an exciting place to be for these experiments, that now finally we're kind of in a regime where we can't do the calculations anymore, even though the Hamiltonian we know exactly. OK, so with that, I'd like to conclude and thank the The members of my group, in particular Peter Brown, this graduate student, has been leading these experiments together with Debayan and Elmer, and Peter Schaus is a postdoc on this experiment. And we've had a lot of theory help from the group of David Hughes, who helped us with the modeling, the group of Yuri Kokolj, who did the finite temperature line shots, and the group of André-Marie Tremblay, who did the dynamical mean field theory. And thank you very much.